All right, so it's Unit 3, and our third unit of AP Calculus BC together deals with applications of the derivative. Not that we haven't been applying the derivative, usually in the context of a tangent line, finding a tangent line to a curve at a point. But in this unit, we deal a little bit more with some of the consequences of the derivative. And one of the most obvious consequences to us as calculus teachers is the idea of extrema of a function. When is a function at its highest? When is a function at its lowest? Where's the top? Where's the bottom? That becomes a big area of concern for us. And so we are going to dive into that over the next few lessons. All right. Here we go. Let me give you a definition. Let me define what I mean by absolute extrema. Some say extrema. They're fine people too. No terrorists in that bunch. We're going to let f be a function with domain D, then f of c is the absolute max value on D if and only if f of x is less than or equal to f of c for all x in D. And it's the absolute min value, f of c is the absolute min value on D, if and only if f of x is greater than or equal to f of c for all x in the domain of the function. This almost makes sense, but of course, this being school, we don't think, so I've got to make us think. F of c is the max if f of c is bigger than any possible f value anywhere else on the domain. This makes sense. F of c is the min if f of c is less than or equal to any other conceivable f value. That's all that definition says. You're the absolute max value if you're the biggest possible y value for the entire function on its domain. That's what we mean. Extrema, hit next page. Don't even. I'm going to pause this for a moment. Sorry, had to take care of a quick little something. Okay, so extrema can occur at interior points. That's a terrible occur. Extrema can occur at interior points or at endpoints. You could have a function whose max and min occur at interior points of a domain. You could have a function whose extrema occur at endpoints of the domain. And of course, you could have a function where the max and the min occur at interior or endpoints or some combination of the two. Furthermore, it is not necessary to have extrema on a domain. I present the following three examples of functions that do not have extrema on a domain. If we look at the red function has neither a maximum value nor a minimum value on its domain. If you say, well, let's say this goes up to 5. 5 is the absolute max. Well, it can't be the absolute max because 5 is never attained as a function value. We get close to 5, we don't get 5. So then you say, well, 4.99999999999 is the absolute maximum value. Yeah, but we get closer to 5 than that. Well, okay, it's 4.999999999999999. And as soon as you stop talking, I can get closer than that. So when you see the open circle at what's supposed to be a max or a min, you don't have a max or a min. It is not necessary to have extrema on a domain. So this has no max or min. Same thing happens at the bottom end. This has a max but no min. And same thing over here. This function has a max but no min, because whenever you think you have a min, well, we can get smaller than that. Now, notice what happens to blow the extremum out of the water is that the red and the green and the blue down low on this slide here are all discontinuous somewhere, which leads us to the following theorem. If f is continuous on the closed interval AB, then f has a max value and a min value on AB. If f of x is continuous on AB, then there has to be a max and there has to be a min. There is no way around it. Because the only way I can think of to blow the possibility of an extremum is to have somehow we'd never get there because there's an open circle or an asymptote or something along those lines. Okay, there we go. There we go. So that is a giant theorem. If f is continuous, then f has a max value and a min value on AB. So how do we find them? Well, really, there are two kinds of extrema. Really, consider this function on the closed interval from A to B, and consider maybe that's C, maybe that's D, and maybe that's E. This point right here, this is what we call a local max. Some textbooks refer to this as a relative max. And when we say local max, we mean that that value, this value right here, f of c, is the highest y value in some open interval containing c. I can draw an open interval containing c. The actual technical term for that is a neighborhood. I can draw an open interval containing c such that f of c is the biggest y value in that open interval. If that's the case, we've got a local max. It's not the absolute max. The absolute max is going to happen over here. This is the absolute max, which also happens to be a local max. Because if you are the absolute max, then you are also a local max, because I can draw an open interval containing point E for which that y value is as high as we get in that open interval. Similarly, at D, we have a local min. F of D is a local minimum value. X equals D is the location of the local min, or if you like, a relative min. because I can draw an open interval containing point D where that point is as low as we go. It's not the absolute min. The absolute min is going to happen over here. F of A is the absolute minimum value of the function. It is also a local min. And in fact, for that matter, this thing. At f of b, we have a local min. F of b is a local min value because I can draw an open interval containing b, and we don't have anything on the right side of b, but I can draw an open interval containing b for which that is the lowest y value possible. So some folks refer to local mins as relative mins, local maxes as relative maxes, but that's the vocabulary. That's what we're shooting for. So here's the thing. What do you notice about the tangent line here, and the tangent line here, and the tangent line here? Right. Those tangent lines are all flat. So, theorem. If f has a local extremum, either a max or a min, at an interior point, call it C, of its domain, and if f prime of C exists, then f prime of C is 0. If you can draw a tangent line at a max or a min, if you can draw one, it's flat. Two things this does not say. Warning, 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 warning. Two things this does not say. One, it does not say that f prime of C has to exist. You could very easily have a situation where f of C is the absolute max on a domain, but f prime of C does not exist. Similarly, this does not say that if f prime of C is 0, then you have a local extremum. That logic does not work. Consider x cubed. At x equals 0, we have a flat tangent line. But we clearly do not have a min or a max. So for all you people who have stepped away or will print this out later or whatever, on the left we have a situation where f prime of C does not exist, but we still have a max. And over here on the right we have a situation where f prime of C is 0, but there's no extremum there at all. So we've got to make sure the logic is right. If there is an extremum, and if the derivative exists at that extremum point, then the derivative will be 0, but not the other way. Not if the derivative is 0, then we have an extremum. So how do we find extrema? Well, this is actually not too bad at all. Local extrema will only occur at endpoints of the interval or critical points. And critical points, for those of us who are really good with our vocabulary, critical points are values where the derivative is 0 or where the derivative does not exist. If I'm looking for local extrema on an interval, they will only happen at the endpoints of the interval or at a critical point inside. So, when I ask you to find the absolute extrema of f of x is x to the 2/3 on -2 to 3, the absolute extrema, those are the absolute max and absolute min values. I know that those extrema will either happen at f of -2 or at f of 3 or at f of some critical point inside the interval. Well, pretty clearly, f of -2 is the cube root of 4, and f of 3 is the cube root of 9. That's 2 squared and 3 squared for those of us that remember our laws of exponents. And so now I've got to know if there are any critical points, any places where the derivative is 0 or the derivative does not exist. So I take the derivative. And I recognize that the derivative is 2 over 3 cube root of x. Pretty clearly, there is no value of x for which that derivative will be 0, because its numerator is 2. But there is a place where the derivative will not exist, and that's what happens at x equals 0. At x equals 0, the derivative is undefined. And sure enough, if we substitute 0 into the original function, we get a y value of 0. So once we have the endpoints and any critical points, we can make a determination. The biggest of those three y values is this one. And so we say that the absolute maximum value is cube root of 9, and it occurs at x equals 3. And similarly, we say that the absolute minimum value of the function on that interval is 0, and it occurs when x equals 0. The y values are the maximum values or the minimum values. The locations where they occur are x values. And there is how to find extrema on a closed interval. Now, this is a big deal because I'm going to be asking us to find extrema for the next couple of weeks. And so you've got to have in your mind, I check endpoints, I check critical points. I check endpoints, I check critical points, because that keeps coming back over and over again, like I will starting tomorrow. All right, bye.